guys, it's Lizzie, and today we're going to be going through related rates. So the problem reads, water is leaking out of an inverted conical tank at a rate of 10,000 cubic centimeters per minute, at the same time that water is being pumped into the tank at a constant rate. The tank has a height of 1,000 centimeters and a diameter of 200 centimeters. If the water level is rising at a rate of 20 centimeters per minute, when the height of the water is 300 centimeters, find the rate at which the water is being pumped into the tank in centimeters cubed per minute. Okay, so the first thing I'm going to do is label my cone. Instead of going diameter, I'm going to go radius. There we go. And that's going to be 100 centimeters. And for my height, it's going to be 1,000 centimeters. All right. We find that from here, 1,000 centimeters, diameter of 200, which I just divided in half again. From here, as we read on in the problem, we know that water is being filled into the tank, but we don't quite know how high or how much of it. So we're going to say that we have another R right here, and that water has a height of H. All right. So now we're going to focus on our goal. What are we exactly looking for? As we read the problem, we see that in the last sentence it says, if the water level is rising at a rate of 20 centimeters per minute, when the height of the water is 300 centimeters, find the rate at which water is being pumped into the tank in centimeters cubed. Okay, so what exactly does that mean? So we're trying to find how much water is being pumped into the tank, right? But we don't have a direct way to get there. So we're going to have to find the total volume of the tank first and then subtract from there. So we're going to be looking for dV over dt. That is equal to the amount of water going in, water in, minus water out. We do already know one of these variables though. We know how much water is coming out of our tank. This one, we know that it's coming out of the tank at a rate of 10,000 centimeters cubed. So we can immediately just put that right in. Water in minus 10,000 centimeters. Okay, so this is what we're solving for. We're going to solve for dV over dt and then subtract it, or I guess add because we're solving for water in. All right, now what do we know? So we do know the equation for the volume of a cone. So it's going to be V is equal to 1/3 pi r squared times h times our height. So from there, what do we know? So we're going to need to know r, and we're going to need to know h. And of course, we're solving for V. We already know that. So we're going to solve for r. So we're going to look all the way back to our pre-existing triangle. Okay. So r is going to be, because the two triangles are similar, or they're the same, but just on a different scale, we can set them equal to each other. So we're going to say 100 over 1,000 is equal to r over h. So we're going to keep the radiuses together, and we're going to keep the heights together. All right, so now we're going to cross multiply. It's a terrible arrow. I'm going to cross multiply and get 100h is equal to 1,000 r. So we are solving for r, so we're going to divide by 1,000. And then simplify, and we're left with h over 10 is equal to r. I'm going to move this work over here for now and just say that we know that r is equal to 1 over 10 h. So now that we have that, we can't solve for h in r known, but we can solve for h in r when. Because if we look back on our problem, it does say if the water level is rising at a rate of 10 or 20 centimeters per minute when, the key word is when the height of the water is 300 centimeters, find the rate at which, blah, blah, blah. Okay, so when, we do know that h is equal to our height, and our height is 300 centimeters. So we're going to automatically put that in 300 centimeters. And we do know that our rate is 20 centimeters. So that's going to be our dH over dt is equal to 20 centimeters. All right, so I know that there's a question of why don't we need dr over dt, or at least that's what I was wondering. We don't need that because r is a constant. We already know what r is in relation to our triangle, whereas we don't know what h is at the same point as r, if that makes sense. So we know what h is only in regards to the 20 centimeters. So they have to be together in order for us to use them, versus the r, where we can just use it without our two h values. All right, so now we can use our equation. Or I guess we don't need this. Now we can use our volume equation. So we know that volume is equal to 1/3 pi r squared times h. And we already know what our r is, so we're going to automatically put that in right now. R is 110 h times h. Oh, that's squared. So now we're going to simplify. We get volume is equal to 1/3 pi times 1/100th h cubed, because we're going to combine, this is going to distribute in, and then we're going to combine this h. All right, and now we can simplify even further. Volume is equal to 1/300 pi h cubed, or I guess pi can go on top, h cubed. Now we can take the derivative of our equation. All right, so it's going to be dv over dt is equal to 3 pi over 300 h squared dh over dt. And we know all of these values. So we know our, let me get a different color. We know our dH is going to be 20. And we know our h is going to be 300. And then we're solving for dv over dt. Okay, so we know dv over dt is equal to 300 pi, or 3 pi over 300 times 300 squared times 20. All right, so we know 300 squared is 900. 900 times 2 is 18,000. And we can simplify our 3 and our 300, so it's going to be pi over 100. 1800 pi, 18,000 pi over 100 is equal to dv over dt. That's still what we're solving for. So now we're going to simplify 1, 1, 1, 1, and we get 1800, 180 over 1 pi is equal to dv over dt. So then we have our dv over dt. We can go all the way back up to our goal and solve for our goal. So we have 180 pi is equal to, I'm going to say x minus 10,000. We're going to add to both sides. And we're going to solve for x. So our x is equal to 180 pi plus 10,000. I guess it's centimeters cubed per minute. All right, and that's our final answer.